Welcome to today's webinar on how to increase runtime and reduce size of solar-powered IoT devices. My name is Furkan Noor. I am an applications engineer in Maxim Integrated. My main area of work is power electronics, and I have been working in developing power supplies for automotive, industrial, and data center markets. Joining us today is Frank Dolling, who will be presenting this seminar. Frank Dolling joined Maxim in 2010. He has more than 20 years of experience in electronic industry in roles ranging from business development and engineering development. He is currently responsible for leading Maxim's wearable solutions initiative for power management, as well as multiple other product lines. Now I invite Frank to start this webinar.
Thank you, Furkan, for the introduction. Welcome to the webinar today, where we will be looking at a new approach for powering Internet of Things devices, particularly small space-constrained devices. Now, Internet of Things is something that's been talked about for some time, but I believe now there's some momentum gathering around the possibilities. There are a lot of new low-power sensors in development to measure many more types of data. And Maxim is actually in the forefront of developing some of those new sensors for biometric data. On the communication side, there are new options to get that sense data up to the cloud. New low-power wide area networks such as LTE/Cat-M1 or narrowband IoT or the LoRa network. And just over the horizon, we have 5G. So the momentum is opening up the possibilities to measure more things and to measure those things further afield. The question I want to consider today is how to power these more dispersed IoT devices. So one obvious candidate could be solar energy, particularly if the IoT device is exposed to a good source of light. Now, harvesting solar energy is not new. Solutions such as the one illustrated on this slide are common around the world. But these existing solutions are not really optimized for those smaller, space-constrained Internet of Things devices. And I've illustrated some examples on the right, from wearable healthcare devices, both fitness and medical, the small remote sensors or asset trackers. It's hard to imagine a solar panel like the one on the left being used to power the products on the right. Now, although these products seem like very different devices, they do face common challenges. Remember, we are considering space-constrained devices here, so they're usually trying to keep their physical size to a minimum. Whether the IoT device is placed on the wrist or on a valuable asset that's going to be tracked, there is a limit to the size that can be tolerated. But at the same time, these devices are trying to maximize the runtime, either from a single battery charge, if the device is rechargeable, or from a single physical battery if they are not. For example, your IoT device that is remote is powered by a physical battery. You want that runtime to be as long as possible so that you don't have to roll a truck to replace or service the battery when it dies. So these are the two main constraints that they're trying to do: minimize the size, maximize the runtime, and all the time there are these increased power requirements coming on these devices as the functionality increases, more data being monitored or collected, more data being transmitted. So how do you increase the power capability? Increasing the battery size is not an option if that design is space constrained. To resolve these conflicting challenges, one way could be to supplement the power using an alternative energy source such as solar, topping up that rechargeable battery while the device is running, providing an alternative supply over a supercap for primary cell systems, or if the power budget allows, powering the whole system from a solar-based solution. But to do that, we believe that what was needed is a small solar harvesting solution that is efficient and that is tailored for the size of solar cells that these kind of devices can actually incorporate. So we believe that the MAX 20361 is designed to meet those challenges. So first of all, it's small. You can see that the WLP package is a 1.3 by 1.63 millimeter package. But not only is the device small, but we've designed it so that it can operate with smaller and fewer external components. As you can see, a 2016 4.7 microhenry inductor. So the two features together, the package and the fewer external components, basically together give the smallest PCB footprint for solar harvesting in the industry by a wide margin, about 50% smaller than what's existing on the market today. And you'll see that the device here is designed for efficient harvesting between 15 microwatts and about 300 milliwatts of input power. So it's tailored for a smaller solar cell. You're going to get a lot more power out of a solar panel the size of a desktop, but these devices aren't going to be using those kind of solar cells. They're going to be using smaller ones, and you want something that's optimized to run from a smaller solar cell type source. So that's the size. The second thing is it is more efficient than anything on the market today. You see here we are in the mid-80s of efficiency for boosting from an input of 0.7 volts when the source current is in the tens of milliamps, which is where you want to be. And that's about 5% better raw efficiency than anything else on the market today for this type of application. Now, of course, that efficiency drops when the source current drops as well, but it's still pretty good in almost to the 70s. So that's just the raw efficiency. But there's a couple of other features in this device that helps increase the overall system efficiency as well. So the first of these is actually that it is optimized for a single cell or 2 or 3 cell architecture, so low cell architectures. You can see here that the VIN goes from 225 millivolts to 2.5 volts. I'm going to talk about how this low cell count can improve the overall efficiency later, but just bear it in mind for now. And the second contributor to this improving the system level efficiency is a combination of two other elements. The first one is the adaptive maximum power point tracking block. So maximum power point tracking is a common technique to maximize the harvested energy from a solar cell at any given time. But there are a couple of input parameters to this MPPT, which MAX 20361 has actually made adjustable. And these adjustable options give the system plenty of scope to fine-tune the MPPT operation to maximize the harvested energy at any time. But how does the system know if these adjustments are helping or if they're even appropriate at any given time? So that brings me to the second element of this combination, which is this integrated harvest counter. Now, that integrated harvest counter gives a real-time indication of the charging effectiveness of the solar system in real time. And now, it's important to stress that the harvest counter will not provide an empirical measurement. It's not going to tell you how much harvested power you're doing in milliwatts. What it provides is a relative indication of whether harvesting is improving or deteriorating. And that's enough to make the system smarter in making its decisions about what to adjust and how to adjust it. I'm going to go a little bit more detail into that later in the presentation. But let's get back to those conflicting requirements I talked about earlier for these space-constrained designs. So you're trying to minimize size. We've tried to make our solution the smallest in the marketplace. 50% smaller than anything else. Now, you still have to increase the PCB area to add this solution. So you are needing to invest something to try to get this alternative source. But having an alternative source will help you maximize that runtime from that single battery or from that standard battery. And what we try to do is not only will you get that extra energy, but we're going to be more efficient at translating that those solar photons into system energy that the system can use, up to 10% more harvested energy from this solution than anything that's on the market today. The second thing I want to talk about now is this is also optimized for this single or low cell architecture to minimize. The reason for this is it minimizes the interference from shading. So I'm going to try and illustrate that with this slide. Here we see two solar cell architectures for a wearable healthcare device. Imagine this is the watch face, and on above we see a 6-cell in series architecture, which we've arranged in a simple pizza pie formation. Now, 6 cells in series has been a common approach in the industry because it brings the total cell voltage to 3 or 4 volts, which is a very easy voltage for those systems to handle. And below we see the other extreme, the lowest cell count possible, a single cell. Now, we're talking about design challenges in shaded conditions. On a wrist-worn device, there's definitely a big proclivity to shading, and the most likely candidate is, of course, the wearer's sleeve. So here I've added the sleeve here, and in this example I've used very broad brush mathematics only to give you a sense of what's at play here. But let's imagine the sleeve is covering 42% of the watch face. Now, this shading severely limits the 6 cells in series approach and its harvesting capability because the source current is limited by the most shaded cell and the conductance that it allows. So you can see here this cell here on this pizza slice is down to basically exposure of a very tiny triangle close to the center. Now, the current in 6 cells in series, of course, is limited by the most shaded current. So it's equivalent to having all of these pizza slices similarly shaded. So all the photons that are, for instance, landing on these other 3 cells on the right-hand side that are fully exposed to sunlight cannot be translated into cannot be harvested because the current is limited by this most shaded cell. On the single cell, it's a very, very different approach. Basically, it's a what you see is what you get. If you're 42% in the shade, then 58% of the cell that's exposed to direct sunlight is harvesting as normal. So you can see here, this is a real common life occurrence on a wrist-worn application. And you can see that there's a significant harvest efficiency difference between the two approaches. Now, shading effects will be more or less important depending on the application, but a similar effect could be imagined for an outdoor remote sensor. Now, this picture does not particularly look like a space-constrained device, but let's imagine this is a sensor here, and it's space-constrained, and we have 6 cells in series, single cell. I've used a very fanciful shading effect here, 1 leaf, but you see a similar effect here. The harvesting ability of the 6 cells in series is limited by the most shaded cell. And maybe even a better way to think about it is imagine the shadow from these trees creeping across this solar cell here. As soon as this first cell here is fully in shade, it's the same as if they're all in shade, because it's the most shaded cell that determines the current that can be harvested from this 6 cell in series. Again, with single cell, what you see is what you get. And if there's 70% in direct sunlight, you'll get all of that energy ready to be harvested. So I think that helps illustrate how these single and low cell architectures can contribute to a higher efficiency for applications that are prone to shading. And the more energy you can harvest, the longer the runtime you can donate to your system. The second element on the system level side that I want to talk about, which I mentioned earlier, is the combination of this adaptive maximum power point tracking and the on-chip harvest counter. So one way to look at this is that you have some parameters that can be adjusted, and then you use the harvest counter in the background to supervise whether these adjustments make sense and whether they're making a positive impact. So as I said, the MAX 20361 utilizes maximum power point tracking. And one important parameter MPPT utilizes is the open circuit voltage of the solar cell, which I'm calling here VOC. But how VOC is determined and applied can make a great difference to the effectiveness of the MPPT mechanisms. So I'm going to illustrate that very, very quickly here with one aspect of how this might work. So one of the things we can adjust is the recalibration period. So to maximize the harvesting efficiency, you really need to have a very good indication of the open circuit voltage for a given condition at a given time. And to do that, you really have to recalibrate regularly. But monitoring the VOC is inherently inefficient because it costs you energy. It costs you energy to make the measurement, but it also costs you energy because you have to disconnect the cell from harvesting in order to measure its open circuit voltage. So in a sense, the system is donating a bit of energy back to make a measurement in the hope that it will reap the benefit of having more efficient harvesting. So is it worth recalibrating at a given time? The answer is it kind of depends. If conditions are changing, then yes, probably. If your IoT device is on a container on a train that's running through the Black Forest and it's going through shaded and clearings and shaded areas and rapidly changing lighting conditions, then it's probably a good idea to update that VOC very regularly. If that container is then parked in Strasbourg train station for 3 hours in the broad sunlight, then the VOC is probably not changing and the harvesting is probably going on very, very well without any recalibration. So if conditions are not changing, you really shouldn't be looking at the VOC every 3 seconds because overall that's a waste of energy. So how is the system to know what's happening with the harvesting? Well, that's where the harvest counter comes in. In a sense, that it makes the system aware of those changing conditions. If the harvest counter is staying pretty much at a constant rate, then don't bother recalibrating the VOC. If the harvest counter is changing rapidly, then maybe you should be recalibrating that VOC more frequently. So that combination of harvest counter and an adjustable parameter, I think you can see can really improve the overall system efficiency. So that's just one example, but there are other techniques that could be applied to basically correct for variation across different solar cell types or even variations between individual solar cells. The combination of having adjustability and a real-time feedback on that adjustability in the harvest counter is a very powerful tool to improve the overall system efficiency. So the MAX 20361, we believe, is the smallest solution in the world. It's the most efficient solution, and it's smarter than any solution that's been on the market to date. So we believe that this device really changes the calculation for these small space-constrained devices to actually allow them to add a solar energy component to their power supply. It costs less PCB area to add, and it's more efficient at harvesting the energy, and it's tailored for these small cell sizes, physical small cell sizes that these small devices can carry. So, of course, every system will vary. The power requirements will vary. The light sources, whether it's going to be a lot of time in the outdoor sunlight, whether it's going to be the whole time in a hallway in a hotel somewhere. But so your systems are all going to change and have different requirements, but I trust I've given you a flavor of what a harvesting solution based around the MAX 20361 could do to increase the runtime of your system. So that ends the presentation portion. Thank you very much for your attention. And I would like to pass it back to Farquhar now for the Q&A session.
Thank you, Frank, for that informative presentation. Before we start Q&A, I want to draw your attention to the Contact Us window on your screen. If you'd like additional information what was covered today, please fill out the form and we will reach out to you by email. We have a lot of good questions that have come in, and the first one is, are there solar cells you recommend for these solutions?
I like to think we're actually solar cell agnostic. We have customers looking at all types of different solar cells with this solution at the moment. And even on the EV kit, we do include a solar cell on the EV kit, but we also give you the capability to connect in a cell of your choosing as well onto the EV kit. So nothing in particular is recommended. We're pretty open to different types.
Okay, we have another question. What about the thresholds to stop charging the battery and capacitor? Are these thresholds programmable?
Yes, we do have a couple of thresholds that are programmable. There's a programmable battery termination voltage, and basically that will stop harvesting when the battery. So the MAX 20361 will monitor. We call it the sys pin, but it's basically connected to the top of the battery in a rechargeable battery situation. So there's a battery termination voltage that's programmable over I²C. And basically when the battery voltage hits that, it'll stop programming. And there's also a battery recharge threshold voltage that's programmable. So when the battery then drops back down to that lower voltage, it can then start to recharge again. So there's a couple of programmable breaks in the device.
Thank you for that detailed answer. We have another question. What supercapacitors can be used? Are there any recommended ones, or what are the parameters someone needs to see while selecting a supercap for this application?
Okay, so on a supercap, so the boost output, the output of the MAX 20361 is programmable between 4 volts and 4.7 volts. So if you're going to put a supercap there, you need to have one that has a rating in that range. And I think that's a pretty common rating for supercaps, particularly used in the metering industry. So that's a common one. So that's, I suppose, the main parameter you have to look out for. In terms of size and dimension and capacity and so on, that's probably going to be more dependent on what the system needs are, what the instantaneous current is needed, how much current at any one time, and so on. So that's probably more to do with the system than to do with the MAX 20361.
Great. We have another question. Do you need a special lens?
A special lens? I presume that means solar cell, and that basically goes back to the first answer I gave. Probably we are open to a lot of different types of solar cells, as I mentioned. So I think that's a similar question to the one that came before.
Okay. Then we have another question. Which PMIC is better companion chip for MAX 20361?
Okay, so there's the very simple architecture to be a companion chip is you basically have a PMIC and the solar charger, and they basically are both individually able to charge the battery. And that means that this MAX 20361 in this kind of architecture will basically work in tandem with any PMIC or any charger. One of the disadvantages of that architecture is that, of course, as I sort of mentioned earlier with the question on the termination voltage, when the battery is full, there's certain periods when the battery cannot or should not be recharged, like when it's full or it hasn't got down to its recharge level. At that time, you basically would switch off the chargers, both of them, and that means that anything that is harvested at that time, that energy is thrown away. Maxim does have a new PMIC, the MAX 20360, which is designed to actually work seamlessly with the 361 together, so that the control of turning off the charger and the battery termination is all controlled from the PMIC directly to the 361. The second advantage is there is thermal supervision in the MAX 20361. You might have seen a thermistor connected to the device externally on the circuit diagram that I showed, or the block diagram that I showed. And that's there to make sure that the charging will stop if the device gets too hot, if the system gets too hot or if the system gets too cold, for safety of the battery. If you use the combination of the 361 and the 360 together, basically you don't need a separate thermistor for the 361. Again, it'll be controlled from the PMIC. And the third advantage, and you have to remember a little bit earlier in my answer here, I'd mentioned that there's a point where you turn off the solar charger and it can't charge the battery. Well, together with this PMIC, what we've done is we've put in a little system that if the solar charger cannot charge the battery, we will basically make that energy available. The PMIC will make that energy available to the rest of the system. So that means that any harvested energy is theoretically always being used. There's no point where the harvester really needs to be turned off. That's a very long, complicated answer, and a lot of fist explanations as well. But I hope I got the message across.
Yeah, thanks, Frank, for this detailed answer. We have a lot of questions, but we are running out of time. But I want to take a very interesting question, last one maybe. What happens at night?
Okay, so what happens at night? Well, there's two automatic mechanisms in this device. One is to basically the device will shut down automatically if the VOC drops below a programmable threshold. So this is where basically when the open circuit voltage of the solar cell is so low that the system decides that there's not enough energy to be harvested, it's probably not worth harvesting anything, let's just go to sleep. So that's kind of a sleep mode for low light conditions. Now the harvester also can also be shut down. So it can be shut down by an enable pin, or it could be shut down by an I2C command. So that's another way. That's then a full shutdown mode. Now the sleep mode still uses a little bit of energy. The shutdown mode uses less energy. Let's say a wearable device that monitors sleep will know will realize when the wearer is asleep, and we'll probably then decide that it's probably a good idea to totally shut down any harvesting that's going on. So there's a couple of options to basically reduce the power. One of them is automatic. One might need a little bit of system intervention, but they basically will give you a couple of options to make sure that you're not trying to harvest under conditions that are not going to be very fruitful, such as at night.
Great. So that's all the time we have for today. Thank you for joining us, and thank you for all of your great questions. Thank you to our presenter, Frank. If your questions were not answered during the webinar, we will answer it via email. And after the webinar webcast ends, there will be a pop-up on your screen for an opportunity to request a meeting with our team. Thank you for joining us.
Thank you.